All right, so when I was preparing this talk, I decided that since the paper's out and since I gave a fairly standard talk a good number of times, I would switch it up a bit and give something a little bit different. Also, since this is a symplectic group that's not afraid of pseudo-holomorphic curves, I thought I'd spend some time talking about pseudo-holomorphic curves and those aspects of the proof. Still, though, I want to state the main dynamical result of this joint paper with Helmut. So everything that I'll talk about today is joint with Helmut. Right, so here it is. Theorem, consider R4 equipped with a standard symplectic structure and a smooth Hamiltonian, for which it's the case that if we define this manifold M as H inverse of 0, and this we want to be a non-empty, compact, regular energy level. And then under these assumptions, the Hamiltonian flow on M is not minimal. So let's see. So I'll explain this and we'll move on in a second. And I wanted to state this up front because this is sort of, in some sense, the big result, the big visible result from our paper. But in many ways, I think that for people more interested in symplectic geometry and topology, there's something else which is very interesting, which I want to spend most of my time talking about today, which is the pseudo-holomorphic curves which generate this result. But nevertheless, I wanted to sort of state this up front. This talk won't be too dynamical, though. So maybe you're looking at this result and you've forgotten or never known what it means for a flow to be minimal. And basically, a flow is minimal if it's the case that every trajectory is dense in the manifold. So what's an example of a flow which is not dense? Anytime you have a periodic orbit, right? Because that trajectory is certainly not dense, it's a periodic orbit. So this idea that, right, so to say that a flow is not minimal, maybe we're saying there exists a periodic orbit. But if we knew that, then we'd say that, and we haven't said that, so that need not be the case. So right now, I mean, this is sort of one of the interesting things about this result, is that whatever it is that we find, it's some sort of, we guarantee the existence of a closed invariant subset, which is not everything. Yes, Danny?
Do you have an example without a periodic orbit?
Yes, so we'll get to examples where we know that there exist no periodic orbits. We have to reduce the regularity on this, though. I have it's to reduce the regularity in order to get that, but we'll talk about that. Good. So in order to proceed, I want to back up a little bit, just to give a little bit of historical context and say, let's see. Here's the question. Let X be a vector field on S3. Must it be the case that the flow associated to X has a periodic orbit? Question. And of course,
you mean by non-singular, because otherwise it would be wrong.
Well, must it have one?
Must have.
I mean, a constant. We can make it non-singular if you like. Let's be a.
So for example, we take
Non-singular means no or zero. And presumably you've seen this problem before. It's an old problem. It has lots of answers. This is the Seifert asked this question. And in general, we know the answer is no. Basically, you can find vector fields of whatever regularity you like on S3 with a property that they don't have a periodic orbit. There's an exception. Which is the Rabe flow. So this is a flow generated by a Rabe vector field. And in this case, we know by results of, well, I guess so Helmut's 93 paper then sort of guarantees the existence of a periodic orbit in this case for any Rabe flow on S3. Although the tight cases or the over-twisted cases were handled by Rabinowitz?
no, Rabinowitz.
He had the the tight because, yeah.
They cover the tight case.
Right. They cover the tight case, right? So the main addition from a dynamical perspective was the over-twisted case where Helmut made use of the classification, Yasha's classification of contact structures on S3. But what will be sort of interesting is that the techniques that were used there we'll use in the tight case, and we'll try and generalize those. That's sort of the input for what we're attempting to do. So related to this, so this question by Seifert sort of showed up in the early 50s. And it took about 25 years before progress started to get made on it. And there's another question that was made in the late 50s, which is there a minimal flow on S3? This is a question due to Gottschalk. And the answer is mostly just big question marks. We don't have much progress on it that I'm aware of. So there's modifications to the problem where progress has been made, but on this specific problem, just really very, very little is known. And it turns out this is a very interesting problem, by which for now I'll just sort of say interesting people or important people think it's an important problem and have thought so for quite a while. And you might wonder, like, well, why is it the case that there hasn't been much in the way of progress? And the answer is, well, if you want to show something is minimal, you have to show that you don't have any closed invariant subsets, which are either empty or sort of the total space. So, and the question is, how do you find those? What tools are you going to use? Because the reality is that closed invariant subsets in general can be exceedingly complicated, right? They can be just disaster. Hausdorff, they can have sort of fractional Hausdorff measure. They can have a Cantor-like structure, Cantor set type structures. So they're just really bad. And the question is, how are you going to have any tools which are possibly going to find these? So, right. So that's just sort of.
Unless, of course, one has a clever idea and constructs a vector field for which every orbit is dense.
Right. But then still, you need to check somehow that every orbit is dense, I think. By construction. Okay, so that's another direction you could go.
The problem is if that doesn't exist, then you actually need an existence result for closed invariant.
Yeah, exactly. Yeah. Right, so now what I want to do is return to the Rabe case. And in particular, we're going to focus on tight S3. And in this case here, right, there exists this, the contact form on S3 can be induced from an embedding of S3 into R4, so that the image is transverse to the radial Liouville vector field. And that's how you get the corresponding contact form on S3. And then you do something which is fairly standard if you were raised on symplectic field theory, right, which is this idea to stretch the neck. So what we want to do is, so let's see. So for me, this is going to be CP2. And here we're going to have this CP1 at infinity. And then, as it turns out, OK, so I guess I can draw this right here. This will be our embedded S3 sitting inside there. And we had this result. Well, we had this result. So Gromov proved this result in 1985. That sort of says, OK, if you put, you have the Fubini study metric on CP2, and if you use that to tame any almost complex structure on CP2, then there exists a unique degree 1 embedded pseudo-holomorphic sphere, which passes through any 2 points you might like. So you sort of get a foliation of CP2 away from the CP1, where you have this one point where all your leaves intersect. And the interesting thing then is that you can do this next stretching construction. where we take a neighborhood of this S3 and we stretch it, we make it very long. We still have our CP1 up here, and we make all these conditions on our almost complex structure. We add conditions like, let's see, the J applied to the vertical direction is the Ray vector field. And we want the J to be translation invariant in this region here. We can define C to be equal to the kernel of lambda, which is our contact form. And we want J to map the C to itself. And we want it to be the case that if we look at d lambda restricted to C, then this 2 form here becomes positive, definite, or tensor rather, and symmetric. So I think these are all our conditions. And then at the end of this process, right, so the idea is we take this region and we stretch it open. Oops, should go down further. There we go. And so the end of this process you have, for instance, let's try and draw this. I'll have a picture which makes sense if you've seen this stuff before, and maybe not much sense if you haven't. But the idea is that you now have some pseudo-holomorphic curves, then which have some negative end down here, I suppose I should say. Pseudo-holomorphic curve is a map from a Riemann surface into, well, in this case here, well, let me just sort of say an almost complex manifold so that it intertwines the almost complex structure on domain and target. So you look at the image of these, and you end up with pictures which sort of look like something like this, maybe. Right? You stretch the neck. You have, and as it turns out, for any one of the almost complex structures that you put on this case, you can sort of squish this region down here together, embed it back into CP2, and that corresponding push forward of the almost complex structure will still be omega tame, and therefore Gromow's result applies, so that in this picture here, as you stretch the neck, you still end up with these sort of curves which have to sort of run through this region. And then you fully stretch the neck, and you get something which I've tried to draw out a little bit more here, where you have some pseudo-holomorphic curves which sort of intersect some component which in the top, you have some component of a pseudo-holomorphic curve in the topmost piece which has a negative end, and then we have, in this region here, we have R cross, in this case, S3, and we have some pseudo-holomorphic cylinder. And then down to the bottom, we have another pseudo-holomorphic piece, which is correspondingly asymptotic in the positive direction. And it's asymptotic to sort of the usual orbit cylinders. So I'm sort of going to assume that people are sort of somewhat familiar with this, so that I don't need to go over too many details. But what I want to argue is that there's a key feature of the contact case. Right, which is the case that we're sort of describing at this point here, which is that we have automatic energy bounds. So in the HWZ language, there's a definition of energy that I don't like, so I'll change it. But it's equivalent right? So this is my definition of energy, and I'll describe it somewhat geometrically here in a second. Right, the idea is that as long as you're only considering curves, you say for instance the Gromov degree 1 spheres, for instance, then this quantity, as you stretch the neck, will always be bounded uniformly, independent of which curve you pick, and independent of everything else. So this, geometrically, how do I think of this? It just maybe, so I should mention that Taub sort of thinks of energy on pseudo-holomorphic curves in kind of a similar way. The idea is that you have sort of, you have a positive puncture which is asymptotic to an orbit cylinder, you have a negative puncture which is asymptotic to an orbit cylinder, and then what you do is you pick out this interval here. So we're kind of thinking of, this direction here is M, and this direction here is R. And so what we do is we pick out this interval here. We thicken up a level set. This becomes A naught, comma, A naught plus 1 cross M. And then I kind of ask the question, how much, well, I would say how much area does your curve have in just this region? And as it turns out, if you take this two form and semi-compose with an almost complex structure, you do get a Riemannian metric. And so in fact, this is computing area for you, or rather pullback area. And so what we're asking is that the amount of area in this sort of thickened slice is independent of sort of where you, well, not independent, is bounded from above, uniformly independent of where you put that slice relative to your curve. Yep. Good. So then we say, please.
Before you pass to the limit, energy is just the global energy is cohomological, and so that's uniformly bounded. But then somehow when you pass to the limit, you can only bound it on every. So
what I would say is if you use Helmut's, I think it's Helmut's definition of energy, then essentially what you're doing is you're saying, let's see, before you've stretched very far but not all the way, and then what you're doing is you're sort of pushing it forward into CP1, and then you're just integrating sort of the omega on, sorry, in CP2, you're just integrating this omega on some sort of slightly thickened portion. And of course, because the symplectic form evaluates positively on complex lines, you get something which is bounded from above in terms of it's cohomological. The bound from above is cohomological. And what happens is if you use that same formulation, if you use Helmut's same formulation, then that idea sort of carries over essentially just fine. If you use my formulation, you put an extra constant in there, right? You'd say something like, there's I don't want to say it.
I think what he wants to know is, so if you have a symplectic space where it's a like CP2 where it's topologically controlled, now you take that slice and make it larger. Then you can take the symplectic form up to here is fixed and up to there as well. And then you can have different ways how to get from there to there. The symplectic form in a monotonic way. Yeah. In particular, you could go very flat and then have a bump here. And wherever you put that bump, you get that estimate.
Yeah.
Yeah. So you estimated, actually, the right way to view this is you study this J-holomorphic curve with essentially a large family of different symplectic structures which outside of the stretching region are fixed. But inside, you take all kinds of different things.
Yeah, that can be done. I don't like any of this approach, though.
Which you made clear.
So for me, of course, so as I started working on the analysis here, what's most important to me is that I have a fixed metric, and I want my metric to be translation invariant, for instance, right? That's going to allow me to do a certain amount of analysis. And so from that perspective, it makes way more sense for me to take a definition like this as energy, right? Because everything I do is relative to that Riemannian metric that you get, which is sort of automatic once you have your contact form or your stable or even your framed Hamiltonian manifold together with an almost complex structure. It kind of comes for free. And so my attitude was like, okay, let's just make use of this from sort of square one and try and step away from sort of the symplectic perspective, because staying in the sort of symplectic frame of mind here, I think it just disaster happens pretty quickly. And so you kind of have to step away from that, or at least that's what I found helpful. is how we make progress.
Yeah. But so I think when Gromov started, it seemed to be that omega is an important thing, and then you take a J as an auxiliary structure. But I think when you start studying conjecture, you should actually make the J the thing. Then you can find a lot of different symplectic structures which are compatible with it, and which form an R-invariant family. So you have an R-invariant family of symplectic structures controlling the suitably chosen J. So that's a shift. That's a shift, and we even go further here.
The argument is that after next stretching, there is some curve that's asymptotic to some rate orbit, and so there you found your orbit.
Yes. Yeah, so again, just to sort of reiterate, you've got CP1. As long as you have an omega-tamed almost complex structure, you have this sort of near foliation by pseudo-holomorphic embedded spheres, the only singular point at infinity where it's not a foliation. And then you do this next stretching construction, which has some translation invariant almost complex structure, suitably adapted. But if you do that, then you can always take this, squish it into here, and the push forward of your almost complex structure is tame. And so consequently, you get your spheres. You move back in this picture and then stretch all the way, and then see what shows up in the limit. And what shows up in the limit is you have these, in the middle region here, for instance, you'll have pseudo-holomorphic curves which have this positive end, and some work then shows that the positive end, you have to be asymptotic to an orbit cylinder. You found your periodic orbit and you're done. So this had been around for quite a while, and so now we have crazy idea. Replace the tight S3 in CP2, so anything sort of star-shaped, with an arbitrary closed hypersurface. Does the same argument work? I mean, in some sense, you might say, well, it seems kind of plausible, right? I mean, maybe we can sort of adjust this thing so we have, again, our almost complex structure is sort of translation invariant. We have to adapt sort of slightly different because instead of having a contact form now, you have a stable a framed Hamiltonian structure. So this is a closed 2 form on your hypersurface. It has kernel, and then this is sort of this provides a framing on your kernel, and so this is a 1 form, and so this pair is the sort of gadget that you get instead, and so you might say, well, maybe the same thing, the same idea works. So maybe it works, but then there's reality, which says nope. And let's see. There's a theorem by Ginsburg and Garel, which says that there exists a proper C2 Hamiltonian on R4 such that H inverse of 0 is diffeomorphic to S3, and it's a regular energy level and has no periodic orbits. By it having no periodic orbits, I mean the associated Hamiltonian flow has no periodic orbits. So, then comes the bad news.
This is explicit, yeah?
No, let's see. Yeah, they explicitly show that there's no periodic orbit.
Explicit.
or explicit enough. All right, fine.
Yeah, so it's an open question if you can find it smooth.
Yeah, that's not known.
Not known. And they claim they can bring it up to C2 plus alpha, which actually has some meaning in Hamiltonian. So C2 Hamiltonians can be quite arbitrary, and with more regularity you already have difficulties.
Yeah, so there's kind of a hidden plus epsilon here. They claim that the techniques that they use should carry over. There should be no obstruction to increasing the regularity slightly. But they don't, I think, presumably because this was sort of good enough, I think, for this case. So right, so we have this idea, maybe we can stretch and find periodic orbits, but we sort of have this example modulo this sort of regularity issue. We have an example of an energy surface which is S3, but has no periodic orbits. So that seems bad. So then the idea is to say, okay, this is the standard, I think, Hofer follow-up, which is, well, what goes wrong? We seem to have this nice idea, right? It seems like it should work. We have strong reason to believe that it's not going to work. So why not? So, and the preliminary answer is that there's instant loss of energy bounds. So what I said, see if I still have it here, is, yeah, here it is. A key feature of the contact case is that you automatically have these energy bounds. Where I've described the energy in this way, in particular, the way I like to think of it is that in some thickened slice, there's a bound on how much area I have, how much area the pseudo-holomorphic curve has in this region, and that bound is independent of where I take that thickened slice, up or down. So what that means then, necessarily, is as a consequence essentially of this, is that now as you try and do this next stretching, you lose this bound. You lose an a priori bound on your energy, and that means that as you slide around up and down, there's going to be places where the area of the portion of the curve just blows up and goes to infinity. Now, I think generally speaking in the field, I think this sign is relevant. If you don't have energy bounds, you don't have much of anything. No energy bounds destroys so much of the standard analysis, pretty much everything, right? So, ye who enter.
Here.
Ye who enter here.
Well, I think
Yes.
about the various circles of hell of Dante.
Dante's Inferno? No? It's a shame. All right. That joke did not play. All right. So.
There was a conversation as you missed.
So let me try and give a picture description of then to kind of give some idea of how weird this is, and that's kind of what got me started really thinking was that I just got stuck, right? This idea that, you know, what happens when you lose that energy bound? Like, what's going on? Or what could be going on? So here's sort of the top end, and we imagine that maybe you imagine that you fully stretch the neck, right? And if you do that, you know, you still have this CP1 that's sort of hanging around here up near infinity. So it's gonna foliate out some sort of nice, some nice moduli space over here, singularly foliate here. You're gonna have some curves, and then as you progress, like those curves are gonna sort of start to dip down into this negative end, right? So what happens? You know, so I'm going to change this a little bit. So if you dip down, so this path here is going to represent something like a sphere. So this is my minimum, and this is sort of my maximum in some appropriate sense, right? And then the idea is that, you know, you have some family, and they're going to dip down further and further into this region down here. What happens maybe? Well, you start thinking about it, and right? Maybe something like this happens. The squiggliness here, so we see length, so we should think area. And the idea is that in any sort of thickened region here, as you progress through this family, as these curves dip further and further down into this region, it's the case that the length is sort of larger and larger, which we're supposed to think of as the area or the energy getting sort of larger and larger and larger as you might like. So this can happen. And this just looks absolutely disastrous. And so you think, OK, so nothing can be done. And what bothered me most about this picture, I mean, in some sense, you think about it, and something like this, in some sense, has to happen because we have Ginzburg-Gorel. We imagine it can be sort of souped up to the smooth case. Something like this has to happen, because if it didn't, we'd have a periodic orbit. OK.
So even that is not clear, right? Because, I mean, what's the equivalent of your previous kind of stable real structure or whatever, where if you have finite energy, then that means that you're convergent to some periodic orbit at infinity. Like if you're not of contact type, then it's not even clear what finite energy means, or is it?
So finite energy is erased. But my notion of energy now in this case, so what happens is on any given hypersurface here, you still have an omega, right? Right?
But it's not a product type as before.
It's
not just the two form on the hypersurface.
It's a two form on the hypersurface, yeah. And so the idea is that now you have something called a framed Hamiltonian structure, right, where lambda wedge omega is a volume form on your hypersurface, right? On your hypersurface, this is a two form with kernel, and then I can make this non-zero in the kernel, and that's going to give me a volume form on M. And so consequently, and then you can still think of this, the kernel of this guy here we'll still call Xi. It's not going to be a contact structure anymore, but it's still a two-plane distribution. And then I can make J sort of map Xi to Xi, and I can still require, for instance, that omega restricted to Xi, that this is again symmetric, positive, definite. And then consequently, on this R invariant region, then I can talk about an energy, which is again this sort of supremum over sort of all shifts of the integral of, let's see, A0 comma A0 plus 1, A circ U inverse applied to this. This is U star, dA wedge lambda plus omega. And this two form right here is translation invariant. It evaluates positively on complex J complex lines, and so we just sort of add it up. And I look at this, I look at this, and in fact computes area if we look at the corresponding symmetric bilinear form. And so this is sort of a reasonable notion of energy, and this is what blows up. Yeah.
And if you had finite energy, then you know that you're asymptotic.
But it only blows up because of the dA wedge lambda.
Yes, so that's also important. So because this omega arises essentially as, you pull back. So usually we think of there being an omega on the whole symplectic space, which you would write little omega. And I want to write, just to sort of separate it out, capital omega, right? And so we'll restrict capital omega to our hypersurface. We get little omega. And consequently, yeah, so you can look at just the little omega energy, and that will be bounded. So you think, and in fact, that's sort of an important, a really important point, is that you do have these a priori bounds.
Yeah,
that's part of the point. Yeah, it's closed, and it's also the case that it evaluates non-negatively on J complex lines, and also it sort of fits together with, you can sort of, it fits together with sort of, in some sense, it adds up to your capital omega as well.
So if it's not of contact type, you still have the transversal control to the vector field.
Yeah. So the idea here, the way I think about this is, let's see. The way I think about this is this sees kind of area, sort of vertical area, right? Symplectization direction maps to the ring, and then your omega term kind of measures sort of horizontal area.
So in your picture, it's actually squiggling like this.
So yeah. So in some sense, maybe it's actually. Well, so we can actually be really more precise. What happens essentially is if this is the symplectization direction and this is M, then it wraps around in these big sheets. And so what happens is, if you look at each individual level set of your pseudo-holomorphic curve, and you think of a movie as you sort of slide up, you have these loops, and the loops get longer and longer and longer and longer, but they do so very, very slowly, very, very slowly. So your corresponding tangent planes to your pseudo-holomorphic curve, they become sort of more and more vertical, and it looks like it's sort of wrapping around and around. And this gives you some idea of sort of the best way, and in fact this is the way, you lose energy bounds, or what I think of as local area bounds. And that is that if you work in a little region, right, a little ball, metric ball, say for instance, in R cross your hypersurface, the behavior of your curve inside this region is it just sort of, it's little slices, right? Rather than, for instance, inside this little ball, it's something sort of nasty that sort of, is just a total disaster. But that has to be proved, right?
Yeah, so the contact type, when you start with the stretching construction, you have this metric ball, and you can't just see the finite amount of area wherever you go. No. And in this case, because the stuff starts accumulating, you have more and more. There's actually growth, so if you move that ball up, the amount of area in that ball actually goes to infinity. But this exponential growth given by geometry.
Yeah. Any other questions so far?
But in some sense, though, even though there's an infinite amount of energy there, you're saying it's sort of locally, I don't know, is it true each connected component intersected with a little ball has bounded energy?
That's the key. That's the key. That's one of the major components to the paper, right? Is establishing that in fact is true. Yeah. Before we get there, though, there's something that I want to highlight this because there's a couple of key insights into this problem. So I want to tell you the first one, and then the second one is exactly what Barney alluded to, which is that if you think about sort of how bad, and this is one of the ways that I sort of like to think about things. You sort of imagine, how bad could it get, and then try to find the weirdest feature that just doesn't sit right with you, and build off of that. And for me, I said, okay, we know it has to be the case that sort of the energy kind of blows up. What's the weirdest feature about this that I just thought this cannot possibly happen, right? And the weirdest feature for me was to focus on that absolute minimum. Is it the case that if you focus on the absolute minimum as you run down to that end, that the area blows up in a neighborhood of that absolute minimum? Is that possible? And it seems not possible. You imagine, how is it possible for the area to blow up? You say, well, we just sort of said we expect it to be sort of sliding around these sort of slices like this. But if you have these sort of slices, your minimum is down below that. So now you say, no, drop down to the minimum. You say, oh, well, oh, no, I can't do that. Now I have to sort of come in sort of some other path. But if I come in some other path near that minimum, you kind of expect it to be the case that your curve is now sort of mostly horizontal. But if you have a lot of horizontal area, that's controlled by having a priori bounds on this. That can't happen. So it has to then be vertical. But if it's vertical, then you kind of expect it to extend down below the minimum and give you a contradiction. And so this was like the first. This was the first component, the first idea, I guess, the first step to sort of say something's not right here. There must be something kind of interesting. And so that was the first theorem that we proved. Which is essentially to say that if and I'm going to be sloppy just to save time a little bit here. So if it's the case that your omega energy is bounded, so we kind of move outside of the category of just sort of considering curves that are coming from this sort of Gromov type degeneration or the Gromov next stretching type degeneration. If this quantity, if you consider curves more generally which come down to a minimum, but they can be complicated, right? They can have genus, they can have multiple positive sort of positive ends in some reasonable sense, and you focus. So if this height here, for instance, is A0, and this height here is A0 plus R, right? Then. Yeah. Then there exists some large constant C such that the integral of u star dA wedge lambda plus omega is less than c in this region, which is then a naught up to a naught plus r. And then I look at a inverse u on this quantity here. Right, so what am I saying?
C depends on R.
So yeah, C depends on R. C depends on R and all the ambient geometry. So that means your J and your lambda, your omega, the corresponding Riemannian metric you get, and it definitely depends on R. It does not depend on A naught. Everything's sort of translation variant anyway. And it doesn't depend on the curve. And so what this says is that near this minimum, area can't get arbitrarily large. In fact, near the minimum, as long as you stay in this sort of compact distance away from that minimum, you do in fact have area bounds. Right? Now, if you move further away, you still have area bounds, but that area is sort of, the bound gets much larger. Move further away, larger, larger, and larger. Does that make sense?
So C depends on E0. Did it depend? I don't remember.
Oh yeah, it does. It depends on E0 as well. It depends on E0. Sorry. Yeah. So this one does not depend on genus. The omega energy does depend, but that can be on genus, but that can be removed. So C, I should say, is maybe if I want to be precise, then C depends on this, depends on R, it depends on the associated Riemannian metric J, lambda, and omega, and that's it. Right, so it doesn't depend on U. Okay, so that at least sort of says, okay, that's it's sort of good news. That sort of tells me, okay, that this weird scenario can't happen. Well, I suppose I can sort of poll the audience. So does this seem at this point, this should seem at this point, okay, that's slightly interesting, but does this strike you as sort of really interesting? Like, would you be excited when you saw this result?
Okay, you can speak the truth.
Okay. No, but I think it's kind of this interesting question, right? Because it relies on this other idea that I'm polling you just to.
It's a good question because usually you move only in the direction you find it interesting.
So when I stumbled across this this result, I got very excited. And I got excited because I knew at that point that this was a problem worth investing time in. Like that's what it was for me. I was like, okay, this is something I have to spend a lot of time working on. And there's a reason for that. And the reason is target local Gromov compactness. So this is my compactness theorem, is sort of the first half of my thesis. What does target local Gromov compactness theorem tell you? Basically says if you have, say, for instance, a symplectic manifold, you have a symplectic manifold, and it's say compact with smooth boundary, and you have a sequence of pseudo-holomorphic curves with boundary either in the boundary of the target or close enough to the boundary either way, then essentially what you can, and suppose it's the case that the area is bounded and the genus is bounded. Then a subsequence converges, provided you trim away a small amount near the boundary and the target. Now that's essentially what this says. And as a consequence of having this area bound here, right? This is an area bound, and because our curves always have bounded genus, right? The picture now is as I run down, I have a family of curves that are coming up. So I'm still sort of in the top half of my cobordism, and my curves are falling down into the negative end. But of course, down into this negative end, I have translation invariance. I can shift up, focus, and then it looks like I can fix the minimum at a single point by sort of shifting as I move down. And then I have a sequence of pseudo-holomorphic curves with this minimum right here, with area bounded and genus bounded. So I can run compactness here. But then it's also the case that I can sort of increase the width, and I can run compactness. I can increase the width, run compactness, increase, 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 pass to sort of a diagonal subsequence, and then we have exhaustive Gromov compactness. Which basically says that you can iterate this procedure, and it's a very precise way in which you can have, as long as you have area and genus bounds on any sort of compact region, then, you can increase that region, and you can allow your bounds to increase as you do, then you can extract a limit out of all of this. And that limit in this case is going to have a minimum, an absolute minimum, and it will also sort of run up to positive infinity. And so what that means is that once it was the case that I got this area bound, we could then say, oh, we can run target local compactness in this sequential manner to prove some of this sort of exhaustive Gromov compactness and get a limit.
Sorry, why did you draw lots of blue lines? Because those are different components of the same curve?
No, this is to represent a sequence of pseudo-holomorphic curves.
So you want to assume they go through the center of the ball, or something to stop it going to an empty to
It could be. I mean, in some sense, it could be empty. I mean, if you want to make sure that you end up what is right. It's sort of like I could give you a sequence of pseudo-holomorphic curves where, after a finite set, your domain of your curves is empty. I mean, that's kind of a stupid sequence, but I would still say that converges in sort of some sense. Yes, if it's the case that you want to make sure that you end up with a limit curve which is not nothing, then you want to demand it to be the case, for instance, that your curves always intersect some compact region on the interior, say. My plan on this was to discuss target local Gromov compactness a bit more tomorrow for those interested. So there are some sort of technical details, but the idea basically is you're sort of saying, look, I've got a bunch of curves in this region right here. They have area bounds and genus bounds. Then essentially a subsequence converges, modulo this sort of trimming near the boundary. And if you want to be left with something interesting, they better intersect the deep interior. Any other questions?
In some sense, it's an interior regularity state in comparison and so on. There, you trim stuff away, you get the part of the curve which lies in some interior.
So, yes, Ronnie.
So your compactness theory is like the Bayes integration to Gromov's Riemann integration.
Maybe. So the way I think of it is. So my attitude is that pseudo-holomorphic curves really just want to be essentially surfaces. You should think of them as submanifolds, not as maps. From the map perspective, when you prove Gromov compactness, you sort of say, okay, you can have bubbling, you do rescaling, and then you sort of say, what happens if I have a sequence of curves with boundary, and then the gradient blows up as you run to the boundary? Well, you sort of say, I still have compactness if I just sort of trim away a neighborhood of the boundary. But the neighborhood of the boundary there is in the domain of your curve. And the problem is that a neighborhood of the boundary in your domain might sort of, the image of that might be all over the place. And so the key idea that I sort of brought to this was that you can trim essentially in a neighborhood of the target boundary, and then a subsequence will converge in that case, right? Okay.
So I feel the seat, because now it feels that you're done.
Now we're getting started.
We haven't even started yet.
Yeah. So the idea here is but this attitude, oh, we must be done, right, or close to done, is exactly this idea of, oh, I now have a limit in some sense. I've found a curve, right? It has finite omega energy, finite genus. It sort of runs up to the end, runs up to sort of the positive end. It should be the case that it's just going to limit to some closed invariant subset, and we're done. Okay, except it's harder than that. Why? Well, there's a couple of reasons. Remember, we don't have energy bounds. And a lot of properties that are nice, that the pseudo-holomorphic curves have, extend from having energy bounds. So how bad could it be? Oh, if it were only 20 epsilons, Helmut would be happy. It was, let's see, what was it? I think it was 2 to the minus 24, I think. Let epsilon be less than 2 to the minus 24. There's a lot of epsilon over 2 arguments.
But you could have done it.
Yeah, I was not efficient with my, but you know, it's already seemed pedantic enough. Right, so there's this idea of, well, how bad could it be? So let's start asking questions like, okay, you know, we have no energy bound as we run up the end, but we do have this, you know, omega energy is finite, so what could be happening? Well,
And we have some properties.
well, yes, it's properness. It's proper, that's sort of, yeah, that's true. That plays a role. So the first main thing to kind of visualize what could happen is just imagine you have an orbit cylinder, right? In the nice contact case, and you've got sort of a curve which is sort of approximating this orbit cylinder. But it doesn't approximate in sort of a degree 1 sense. Suppose it's like, it's very close to being like a branched double cover. If it's a branched double cover of an orbit cylinder, then it looks like a pair of pants. But maybe it has one connected, you know, its boundary component is connected on the bottom and then disconnected at the top. That can happen. And you can do that with 0, you know, omega energy or d lambda energy. So if you can do that, if you can do that in this case, you can sort of wiggle it and imagine that could happen. And then you end up with something, well, maybe it's the case that I start down, I have one positive end, but then maybe it kind of splits off into sort of 2 things. But then maybe each one of these then splits off into 2, right? Oh, but then maybe those split off into more. And more and more and more and more and more and more and more.
And most of them would have caps.
Well, right. So then the next thing is to say, well, you know, so that's one issue that's sort of.
It could in principle even happen with a cylinder structure, where things start bulging off and stuff flying right in.
Yeah, and you sort of say, well, I mean, but could this really happen? But remember, how does the area blow up? This sort of sheeting effect, right? And so if you have this sort of sheeting effect, you can imagine just sort of a little, you put in a little sort of topological switcheroo here, and then suddenly that, you know, you've doubled the number of boundary components, and then you can do this over and over and over again, maybe. So this is one problem. And if something like that were the case, you'd say, oh God, that means my domain is a Riemann surface minus some infinite collection of points. And that seems bad until I tell you, oh, but it could be worse than that. It could be worse because instead of this being a sphere minus some collection of points, right, some discrete set of points or some countable collection of points, it might actually be a disk minus some collection of closed disks. Your domain of this thing might be a disk minus open disks, and there might be infinitely many of them. I can't rule that out at this point.
Why is it worse?
Your domain is not a punctured Riemann surface. Right? In all, it's always the case that as you run out to the end, your limit, you want to be able to sort of, you know, reparameterize and sort of think, I've got some sort of half cylinder here, for instance, and this would say no.
Yeah, so for example, if you get that something which looks like a plane, it could be, of course, eventually in the contact type thing, it's uniformized by one punctured two-sphere, but it could be uniformized by an open disk. We don't know that.
And so one of the things that's sort of interesting about this is something that this is an idea I've used a lot. It's been very fruitful for me. Is always this idea of let's run some terrible notion of compactness, something that's just awful that everyone would say, well, how is that ever going to be useful? Construct a limit, and then make use of and then use that understanding of how you got to that limit to sort of back up in the sequence and then extract additional properties. So for instance, in this case here, you might say, well, maybe in some sense we have a whole bunch of positive ends developing, sort of arbitrarily many. But then the idea is to say, well, wait a second, what if you backed up in the sequence? So you back up in the sequence, and now this is now sort of capped off by some curve that sort of runs up into sort of the top end of sort of CP2. But at this some fixed energy level here, you have a whole bunch of these loops, maybe arbitrarily many. But the thing is that it's also the case that sort of above this region now, these loops can't come back to each other because then you'd have genus, and our curve started with 0 genus. And if they stay disconnected, well, then they either have to run into the very top, or they have to be capped off by some sort of some disk like this. But then what you can prove, and this is sort of the second thing that we prove in the paper, is that each one of these, if you have capping disks like this, each one contains a threshold amount of omega energy. If you have a threshold amount of omega energy on each one, then you have to have only finitely many. Right? And this works whether or not they're sort of capping in sort of the R invariant region, or if they run into the actual sort of cobordism piece, they also have to capture sort of a threshold amount of energy there as well. That's basic monotonicity. And so that's ruled out as well. And so as a consequence of this, in some sense, you now have an a priori bound of the number of positive ends that you have.
How do I see there should be a threshold for the...
No, that was what we proved before.
Well, no.
The caps.
You have to argue that these sort of caps exist. The only thing that you're sort of, well, okay, so the only thing that you're worried about, right?
But if you have a cap with certain lengths, it has a certain amount.
Yes, that's true.
By the previous step. And then when he backs off, before they develop,
Yeah.
there would be concentration with bounds
Yeah.
of this. But if you work in the stretching construction with an a priori finite amount of omega energy, this number of ends has to be bounded.
Yeah. Do you still want to know why is it the case that we have an energy threshold, an omega energy threshold on these caps, or no?
No, but
Well, I mean, I thought you said that...
No, I didn't prove that. I didn't prove the threshold
I
yet.
thought you said there's a threshold...
oh, I
Like
don't
every
know.
cap from below,
Okay.
from below.
I have an area bound.
From above.
Okay,
From
yeah,
above.
Yeah,
upper
from
bound.
above, exactly.
How do you get an upper bound on,
Yeah,
on
you
these
know.
caps?
Yeah. So each one of so it turns out that the argument that says that sort of the area bound near the minimum is bounded. Right, the full area near the minimum is bounded. There's really that's another sort of thing is in this case there's no up or down anymore. Everything is every which way, which means the same argument works if you have a maximum. That gives you an area bound, an upper bound on area. But now what that means is that every one of these caps essentially has an upper bound on area, right? And so you sort of say, well, basically what you argue is then a compactness argument. And you sort of say, well, is it the case that you can have a sequence of caps like this, zero genus bounded area, which have arbitrarily small omega energy, and you can see that, well, if you did, you'd have to converge to something which was actually sort of a patch of an orbit cylinder, and that would violate having an absolute maximum. That's essentially the argument, right, for the omega energy. And so that rules out this possibility. So now that's sort of nice. You sort of say, oh, okay. You know, I have some finite number of ends. That's great. This is sort of wonderful.
So to recap, you have an a priori bound on the number of these tentacles that are coming up.
Yeah. And that's
Uniform for all sequences.
yes.
Coming from a stretching.
Coming from a yes, coming from a stretching construction. Yeah. So I'm more or less.
But principally, you could find things which just have more and more ends.
Yes. So it depends. Those I think will never arise from a stretching construction.
Right, but abstractly.
Abstractly, such things could possibly exist.
So then at what point did we use the rules of stretching?
Pardon?
So at what point did we use that this came from?
Well, because the idea is to back up in the sequence, right? And sort of say like, okay, well, if we back up in the sequence, then these weird ends haven't sort of run out to infinity. We're backing up, and so now the image of our approximating pseudo-holomorphic curve is living in some sort of, you know, stretched CP2, but we haven't dropped all the way down to sort of minus infinity yet.
Yeah, so he works with curves at CP2.
Yeah.
And makes a stretching construction.
So when you say could happen if it didn't come from a stretching construction, you mean because the omega energy would blow up?
So at this point, let me.
The omega energy would blow up?
No. So if you think about sort of what properties does sort of our limit curve have here, because the idea is to say what properties does our limit curve have, and then use that to define a new class of curve, and you might say a ferrel curve, say for instance, right? And I think the first attempt is to say something like, well, let's see, I should really say 0 is that U needs to be proper. That's the only way any of these curves sort of make sense. You know, you also might want it to be the case that the omega energy is finite, and you would want it to be the case that you have, that the genus is also finite. And you might sort of say, maybe this is enough. And what I'm saying is that I can't do interesting analysis with just these conditions. It turns out that to actually do, like to get, for instance, that area bound that you were mentioning, that connected local area bound, in order to get that, I need to have finitely many positive ends. And so we generalize this notion of a puncture And we want that to be finite as well. And you have to throw in that condition. If I don't, then it screws up later actual metric analysis.
The function is the number of n's.
Yeah, the number of n's, yeah, that you have is sort of you move up. The thing that we ruled out the infinite case with these caps. Yeah? But you could allow to have sort of negative n's as well. That's now sort of okay. But you would have sort of a bound on the number of negative n's as well.
Negative n's you have to expect because in contact type there's a negative side and a positive side. But now here there's no preferred side, so things could explode in both directions.
Yeah. So this is so this very nearly is the definition of a Farrell curve. A curve which satisfies this collection of properties. I'd say that there's one more in this case, though. If you want to add in mark points, then the number of mark points has to be finite. If you want to add in nodal points, the number of nodal points has to be finite. And the number of connected components has to be finite. So some basic topological properties. Number of mark points plus the number of nodal points plus the number of connected components of your domain has to be a priori bounded. And then this is the current definition of a Farrell curve. Right?
And for sequences, you want each of those four to be
Yeah, you'd want to bound on all of these. You would want to bound on all of these. Yeah, uniform bound on all of those if you want to proceed and try and run some sort of compactness again. And in that case, you could then extract sort of, let's see, even in that case, it's possible that you have, it's no dice on an SFT type compactness. And that's only though because you have to allow curves which have both positive and negative ends. And then in this case here, it could be the case that sort of everywhere the energy kind of blows up to infinity. And you can't extract something, you can't extract a curve with a minimum, right, or a maximum, say, for instance. So it gets hairier at that case, but it's already.
So you're saying that 3 does not follow from the 1, 2, and 4?
Genus and punctures. No. No, there's no way for me to, as far as I know, if your curves come from a stretching construction, then the number of punctures that you get is bounded. If you're just talking about sort of walking down the street and someone hands one of these to you, it seems to me that it could be sort of infinite end. So amount of time. I want to say sort of just a couple things. And that is that at this point here, you say, okay, I have a positive number of n's, things still should be good, right? It still should be the case that like, okay, now I only have a finite number of sort of positive n's, maybe it's sort of not so bad, but there's all sorts of very strange things that kind of screw up your analysis. So for instance, there's no reason why you can't have like, in some sense, you can't have like this sort of appear over and over and over again, right? Or worse, like why can't you have something which sort of, as you sort of run out the end, sort of you have these little dips and sort of stupid little things that sort of happen, for instance. Like that too could happen as well. It also could be the case a priori that, at this point here we haven't established that you have like that connected local area bound like Barney was sort of mentioning. So it could be the case that maybe as you run up this end, you focus on some point. You take a sequence of points and you look at the area of a connected component of the curve, which inside this region, and the area could still blow up at this point, right? And so at this point here, you just don't have enough information to be able to guarantee that the limit end of this thing is in fact a nice closed invariant set. It's just not enough. So what do you have to do? You have to work very hard to show that connected local area bound. I can talk about this a little bit next time, or tomorrow rather. And then even then you're not done. You also have to establish that your curves outside of a very large compact set are all immersed and that you have a uniform curvature bound. This also has to get done, right? And then after you do all that, then you're in this very, very nice situation where your curves, even though like your area is getting very, very large, you have this sort of sheeting effect. You have it will be the case that every other nice property that you could have of your pseudo-homomorphic curve is going to carry over, right? Finite ends, in fact, the ends are sort of parameterized by punctured disks, and you have tangent planes which are sort of approximating vertical. Everything sort of looks very nice, but you lose that sort of area bound. You've got nice control in the curvature. Things actually look sort of pretty good. And you might think, okay, in this case then, now I've got my end, and now I'm done. But you're still not done, because it's true that as you run out the end, you can extract a limit, and that limit will be a closed invariant subset. You still have to do additional work to make sure it's not everything. And that requires an intersection argument, right? Something we call the workhorse theorem. So it's a lot of work. But that's where I'll stop for now.